I say if if not everyone, most ones, so the others will come along. So anyway, it's a great pleasure today to welcome Professor Andrew Grant from Mount Allison University in New Brunswick, Canada. So from the very nice part of Canada. So it's mostly undergraduate institution, very strong undergraduate institution. And so very interested in working together with the SCSC. But so he did his PhD with Professor Denny Valenta. So in total synthesis on the total synthesis of quasin and bucinatin. I can never pronounce natural products. They're really awful. But a dead-ahead synthetic chemist like me originally, and then get dragged kicking and screaming into biochemistry, and that leads to all kinds of fascinating areas, materials, chemistry. But in the end, that's, I think, the nice part about synthesis is once you know how to make molecules, you can look into all kinds of interesting things. Did a postdoctoral fellow at the University of Toronto, and then he was in industry here in Italy with Marin Merrill Dow for 3 years here in Italy. Yeah. Then we dragged him back into academics. So first as a research associate at York University, and then assistant professor at the University of Winnipeg, and then they stole him over back to the undergraduate side.
I'll show you a map of Canada here.
Where it is, yeah, because I'm an American, my geography stinks. And so he's been at Mount Allison since 1999. He's been chairman of the Department of Chemistry and Biochemistry since 2011. Took a short break there, but they dragged him back, kicking and screaming, to run the place, but not by accident. So the danger when you do such a good job, they want you back and want you to do it again. But anyway, it's really a pleasure to have him here. He's going to talk about some biotin, mostly chemistry, with a topic that's biochemistry, but a very nice, interesting molecule.
Okay. Thank you, Peter. Thanks for inviting me here to Lyon and giving me a chance to talk about my work and meet some students. We are trying to work out an exchange program between my university and yours. So we'll see how that works out. Let me show you just a couple pictures of where I'm from in Canada. You'll see some of these tomorrow if you come to my lecture, but I might as well show you now just so that you are not so let's see, is that it? So this is Canada and United States. Just for comparison, this is lake. This is called Hudson's Bay, and it's twice the size of France. So 2 of France's could sit in here. These are the Great Lakes, largest freshwater lakes, and I'm from way over here in this part of Canada. So this is the Atlantic Ocean. The Atlantic Ocean's here. Europe is there. And Nova Scotia is a province. We have provinces, not states. Nova Scotia. Newfoundland is a province. This little island is a province. That's Prince Edward Island. It's a beautiful place. They grow lots of potatoes there. And this is New Brunswick. So I'm from New Brunswick and from a town. And I'm from New Brunswick. And our university is up there. I'll show you some more pictures and tell you more about it a little bit more tomorrow. But that's where I am. So how do I get rid of that? I will do that, and I'm going to shrink him, and I'm going to shut the whole thing off.
Okay.
Yeah, we'll shut the whole. Yeah. And
now, one chance out of two, I'm sure I'm going to pick the wrong one. Oh, dear. No. Okay, then, see, they love doing this to us. Hide these as far away from each other as possible.
okay. So I'm going to tell you about a molecule, both today and tomorrow, called biotin. And I'll just draw the structure of biotin because it's not drawn here. But it's this guy. It has a 5-membered urea. It has another 5-membered ring here, which is cis-fused. And it has a 5-carbon side chain. 1, 2, 3. So this is biotin, also known as vitamin H. And some people classify it as a B vitamin, but I call it vitamin H. So this is the chemistry will center around biotin. I'll describe a bit of it. And so, for example, in the paper that you see here, this paper here, all you see in the paper is this part. You just see the 5-membered urea. Tomorrow I will talk about the sulfur, but today we won't talk about anything else. We're just talking about the top part. So that's biotin, and it is an enzyme cofactor. Are you familiar with that term of an enzyme cofactor? So, for example, many enzymes catalyze the reactions that they're meant to catalyze all by themselves. So, for example, our digestive enzymes. When we eat food, it goes to the stomach and intestines secrete enzymes that hydrolyze peptides. So, chymotrypsin, I can't think of some names right now, but many of them, the enzymes work all by themselves. But many other enzyme transformations require a cofactor, another molecule that is not protein to help them do its function. So many of the vitamins are cofactors: vitamin B12, vitamin B6, thiamine, pyridoxal phosphate. These are all enzyme cofactors. So that's what biotin is. It works with about 7 or 8 enzymes. Okay, and it is involved in CO2 metabolism, as we'll find out. So carbon dioxide. It can put carbon dioxide on molecules, and it can remove carbon dioxide from molecules. And it can, in another set of enzymes, it can take carbon dioxide from one substrate and put it on another. So I'll explain that a bit more briefly, but I want to ask you what you know about ATP. A little bit. So let me give you. Can I give you a small background on ATP, because it's central. It's central to this talk. So ATP. Could any of you draw the structure of ATP? Do you know what it looks like? It's adenosine triphosphate. 5-membered sugar ring. On the side. Yes.
On the other side
is the triphosphate. So let me draw that too, just for the heck of it. So here is this guy, the furanoside, the furan ring. I forget always the structure of. Let's see, maybe a nitrogen here and here, with another NH2 up here. And this and that. That's an amino group at the top. and OH here, and then carbon 5 and O, P, O minus, O, P, O minus, O, P, O, O, O. This we would call this alpha phosphorus, the beta phosphorus, and the gamma phosphorus. Okay. Now, can you tell me anything that ATP, a specific chemical reaction that ATP does? And we require ATP. I'm burning, and we burn, I don't know, kilograms and kilograms of ATP per day. Our muscles use it, we have to produce it, and we use it, and so on. But can you remember a specific biochemical reaction that uses ATP?
I don't know the whole structure, but it's the NAD.
And yes, it's coupled. Krebs cycle, citric acid cycle. Lots of things get phosphorylated. And it reacts in many different ways, many different reactions. So, for example, you can have amino acids, and you can have an amino acid which NH2, CO2 minus. Let's do it this way. NH3 plus. So an amino acid, there are a series of enzymes called amino acyl transferase, where this part actually goes here to this phosphorus and displaces that, and now the amino acid looks a bit like this. It looks like amino acid NH3 plus OOP adenosine, okay? And that is useful because then this then is involved in protein synthesis. This unit hooks onto the ribosome, not the ribosome, the tRNA, the transfer RNA, which takes it to the ribosome, and eventually something like this happens. A nucleophile here goes here and does that. So essentially what is happening is that the ATP is turning the carboxyl group into a good leaving group. Okay? So that a nucleophile can attack it and kick it out. And that's what ATP does in a lot of things. It turns OH groups or carboxyl groups into leaving groups. So keep that in mind. Now, a lot of things also, a lot of substrates come in here, and they hit the gamma phosphorus and kick this out and become phosphorylated. That's where a lot of kinases work. So simple substrate hits that phosphorus, kicks out ADP, and this substrate now has phosphate on it, O minus, OH, it's now phosphorylated. And so that's a typical kinase, okay? So now we'll get back to biotin. What biotin does in one reaction is this. I'm going to talk about something called acetyl-CoA carboxylase. Acetyl-CoA carboxylase. So what that does is this. Acetyl-CoA is this in its shortest form. It's an acetyl group with sulfur. It's a thioester, and this is CoA. And CoA is another molecule that looks, it's a nucleotide. Okay, so acetyl-CoA, used in lots of transformations. It goes on to make fatty acids in biochemistry. So what happens in acetyl-CoA carboxylase, it basically goes to this. CoA, sulfur, CH2, OH. It puts a carboxyl group on there. So this requires this enzyme. It requires biotin. It requires ATP, and it requires bicarbonate. So the enzyme, and it makes this molecule, which is malonyl CoA. Okay, malonyl CoA. Malonyl CoA goes on and makes fatty acids and some other things. So this carbon here, this carbon, comes from bicarbonate. And it happens in, so one question is, how does that happen? How does the enzyme and biotin and ATP go to make this? Well, it happens in 2 steps. So step 1 is this. Step 1 has the enzyme plus biotin plus ATP plus bicarbonate. Okay, and basically that's what's going on here. So what happens is this. Some combination, and we'll ignore the enzyme. The enzyme is here. We have these substrates. So what is believed to happen is this, bicarbonate, O minus, OH, reacts with ATP. I'm not going to draw the whole molecule. I'm going to just draw this, O, and O, and ADP. Okay, so what's believed to happen, roughly, this is just a working mechanism, is that this goes here and kicks out ADP, so that makes this guy OP, OH, O minus, plus ADP. Okay, now this is a really interesting molecule here. This is a mixed anhydride. It's an anhydride between carbonic acid and phosphoric acid. So it's a mixed anhydride. And then one of 2 things can happen. Either in the enzyme, a base could abstract this hydrogen. This could go here, and this could go here, and that would give carbon dioxide plus inorganic plus Pi is just that, phosphate, inorganic phosphate. Now biotin comes in, and biotin does this. Biotin, somehow, biotin has to be activated. The nitrogens, there's an electron pair on this nitrogen, and it may come in here and attack CO2 and give what is referred to as N. You should have brought more paper with you. I didn't. And something has to remove this proton and to give O minus, which is referred to as N-carboxy biotin. And that's what is shown. That's what is shown over here, is N-carboxy biotin. That's the first half reaction. Second half reaction is this. And then we can talk about the paper. I don't know if this blue is very good for the board, Peter. Second half reaction is this, is acetyl-CoA, so CoA, sulfur, CH3. I'm going to simplify this a little bit. This enolizes somehow, CoA, sulfur, O minus or something. It enolizes. This molecule swings over to here and decarboxylates. So it goes like this and like this and like that. So it delivers the carbon dioxide to here, and the enol grabs it and makes malonyl-CoA. Okay, now I'm going to show that in a picture. So here's the enzyme, okay, and biotin is hooked here. Is covalently modified through the it's here. Okay, and the first reaction happens here. So biotin goes in here where ATP and bicarbonate are, and then biotin goes in, and it produces N-carboxybiotin. The result of that is N-carboxybiotin. Well, this is where the second reaction occurs. That's a 2. The second reaction occurs, that's where acetyl-CoA is. Okay, acetyl-CoA. N-carboxybiotin, this is a long chain, okay? It swings down into here, loses the CO2, and reforms biotin, so it comes down in here with the carboxyl group on. That's this stuff. It decarboxylates, and this enolizes, and this produces malonyl-CoA. Okay, so the end result is that rather than just the enzyme putting carbon dioxide directly on the substrate, it first puts it on biotin. So biotin picks it up here and delivers it to the substrate here. And it acts like a windshield wiper. It goes back and forth. It goes to here where it makes N-carboxybiotin, and ADP and PI leave, and a new ATP comes in, and so on. And then it swings over to here where the actual substrate is, decarboxylates, and puts it onto the substrate. So it goes back and forth like this, which is sort of weird. Why would it put it on biotin in the first place? So that's what biotin does. That's what ATP is involved in. And okay, that's the general picture here. Now, this paper at the beginning here is from 1985, and it's by a guy named Jeremy Knowles. You should highlight him. Now, he died 15 years ago, but he was a very, very good bioorganic chemist. If you ever read a paper by Jeremy Knowles, you can be assured it's the best. So what he was interested in the first half reaction. How does biotin, ATP, and bicarbonate make N-carboxybiotin? That mechanistically inside this pocket here. So that, okay. And so that's really what I want to talk about for a little bit. Now we'll see how far we can get in these things, because it is fairly. I'm good for several hours, but it depends how good you guys are. So now let me, any questions? Any questions? There's a handout if you need a handout. Or did you get one? You get one. So the real question is, the question in a way, when you look at this paper, is this. It's here. You have biotin, ATP, and bicarbonate. And the question is, in what order do they react? Usually, 2 molecules react, and then the third one comes in. There are very few examples of all 3 molecules coming together doing the same thing. From an entropy point of view, that's highly ordered, and so that's unlikely to happen. So there have been all kinds of theories. I just told you one, that ATP and bicarbonate do this. But so essentially ATP is, we say, is activating bicarbonate. In a sense, it's removing water from it. It's dehydrating bicarbonate. But there have been theories where ATP activates biotin, and that's one of them here, and then reacts with CO2 and so on. So let's look at this. So Knowles writes out 3 possible mechanisms. The first one is basically what I just showed you. Okay, ATP and bicarbonate get together to make this structure that is shown there. And now, instead of it breaking down to carbon dioxide, he basically has this. He has an arrow going from biotin to here and kicking out phosphate. So at this point, even now, it's not known for sure whether it loses CO2 first or whether biotin can attack it. Now, there's lots of questions in here, but the point is really this, is that if you want to carboxylate something with a nucleophile, nucleophiles will have a hard time attacking that one because it already has a negative charge. So a nucleophile, that is going to not be great. So phosphorylate it, and now this is okay. Or if it loses carbon dioxide, it's even better. This is really delta plus because it has these 2 oxygens pulling on it electronegatively. So that's the first one. Now the second one is this. The second one is biotin reacts with ATP. So there you have something like this. You would have biotin and ATP, ADP, and essentially the theory was, well, a lot of the electron density is up on this oxygen, so this is going to do that. And so the phosphorus is now here. Now it's on N, O, P. If you like, what ATP has done here, it has enolized the urea. So now it's in its enol form. Okay, and as you know, enols or enolates are more reactive than the carbonyl compound. So now we have to bring in bicarbonate, and so something like this. But that's the question. Then water, for example, could hit this. Then something like this could happen. So that's mechanism. Is that mechanism 2? I have to be careful here, but something like that. Actually, mechanism 2, I have to be more precise here. Mechanism 2 is actually this. Mechanism 2 is what is mechanism 2? I need my glasses. Mechanism 2 is this. Is sort of O minus OH, and it's an electro. It's a pericyclic type reaction where this can go here, this can go here, that can go there, and eventually that leads to N-carboxybiotin. With another step here. It eventually leads to that. So that's the second mechanism. And the third mechanism is related. Third mechanism is here, makes this. Bicarbonate instead comes in here, comes in here, and then the third mechanism would make this, OH, OP, and this compound, O minus, let me get this right here. Would give O minus, and this is an enolate. This could come down here and go here and make N-carboxybiotin. You with me? So there are these three sort of mechanisms. Where does ATP get involved in? Yeah. Yes, please.
In the second one,
Yes.
then it loses the phosphor because remains attached to
Say it again. So phosphorus gets attached to the oxygen? Yes.
and then it loses again
Yes.
by
By
the other oxygen, the other 12 electrons from the other oxygen come down and then it comes or something like that.
yeah, I think water has to get involved.
Okay.
Yeah, it's not as detailed, but there are easy arrows to go from here to there.
Okay.
But yes, I think water has to then hydrolyze the phosphate off. Or
For these electrons here that come and then
well,
The biotin reorients the phosphate from attachment to the bicarbonate at the is that the alpha? Is that the alpha phosphate? No, that's the gamma phosphate.
yeah.
Attach it to the oxygen on the biotin.
Let's try this. So it would give this, wouldn't it? It would give this, and maybe this happens. This goes here, and something like that. Okay. So for Knowles was how to distinguish between these mechanisms. Okay, how to rule out one or something. So what he chose to do here was he wanted to look at the stereochemistry at the gamma phosphorus of ATP. So so we're back here. We're at this compound. O P O A M P, adenosine monophosphate. So he's interested in the chirality here at this phosphorus, which of course at the moment has no chirality because these are three oxygens. But the idea is something like this. So for example, if bicarbonate, if the first mechanism operates, then bicarbonate comes in here and does that, and that is like an SN2 reaction. That would go with inversion of configuration. So the product would look like O, P. So these two oxygens here would go with inversion. Okay, would swing. It would undergo that Walden inversion. And so the first mechanism, and then that makes this compound here, which is shown, and then the nucleophile attacks this, and this leaves, and there's no inversion going on here. So if you could make the gamma phosphorus chiral, the first mechanism predicted to go with inversion of configuration at this gamma phosphate. Okay. The second mechanism it would be, in the second mechanism, biotin attacks the phosphorus, okay? And that goes with, that would be an SN2 with inversion, okay, to give the intermediate shown. And then this bit that we were just talking about here, where the bicarbonate then attacks the phosphorus, that's also, it's a queer-looking reaction, but that also goes with retention at the phosphorus. We can talk about that after. So the first two mechanisms go with inversion. Inversion in the first step, retention there. Inversion in the first step to here, but this oxygen is not coming in here, it's coming in underneath. And so this oxygen is replacing this oxygen, so that's retention at that phosphorus. Whereas the third mechanism has biotin attacking here with inversion to give this product, and then bicarbonate. Bicarbonate would come in here to do this, and that's another inversion. Let me put, okay. So overall, that's two inversions, and that results in overall retention at phosphorus. So two of the mechanisms go with inversion, one goes with retention. So if you could make an ATP that was chiral here, and you could determine the chirality, then you could eliminate one of the mechanisms. Or you could either, if it was shown to go with retention, that would eliminate mechanisms 1 and 2. If it was shown to go with inversion, that would eliminate mechanism 3. Okay? So the question becomes how to make this chiral. And yes.
Can you know, I don't have much chemistry, so can you define chiral for me?
So, okay, I guess so in carbon, for example, but we're going to use phosphorus. Chiral, for tetrahedral carbon with 4 bonds, the simplest, there are a variety of chirality, but basically you have to have A, B, C, and D. You have to have 4 different groups attached to the carbon. And if that's the case, then this molecule, is chiral, we say, and it's non-superimposable on its on this molecule, C. It's A, B. If I reverse these and make this D and this C, then these are almost the same, but they're mirror images of each other. So the classic example we show are our hands. Our hands are very similar. They have thumbs and fingers, but they are actually non-superimposable mirror images of each other. So our hands are chiral. And so and some molecules are and some molecules aren't. So in this so you basically have to have 4 different groups.
That would explain why you use stereochemistry.
To solve this. So what he does is this. He makes this compound. He's going to make an ATP analog that looks like this: P, sulfur. I don't know if I'll draw the stereochemistry correct just at the moment. O, P, O. So he's going to make sulfur. This, well, we'll look at it. This, one of the oxygens. One of the oxygens is going to be, he's got it this way, so is going to be O18, which he makes as a solid circle. This is going to be O17, which has a line, and this is going to be O17. So so oxygen has 3 isotopes. The common one is 16, but O17 is available, and this is O18. So, well, okay, yeah, I mean, yes, okay, so we will eventually, so here's the thought experiment. The thought experiment, suppose you can synthesize this, and you react it with water O16. Then, because ATP will hydrolyze if you leave it in water, because it's an anhydride. So water would come in here and do this, and that would give you this guy. That would give you P sulfur O16 O18 O17. I don't need the 16. So the solid one is 18, the one with the line through is 17, the clear one is 16. So this is now chiral, okay? And sulfur is isoelectronic with oxygen. And it turns out for ATP and for a lot of molecules, you can substitute sulfur for oxygen, and a lot of the chemistry and biochemistry is the same. So there is no fourth isotope of oxygen to work with, so we use sulfur. So this is now chiral. And we can assign its configuration as R or S, where the lowest priority is put at the back, and so on. Okay? So let me see. The question becomes, well, how to make this molecule, how to make it, and know that it has this chirality and not the opposite. Okay, so it's a stereospecific synthesis. And in the reaction, so we have to be able to make this molecule. It's called this supposed to be P. This is AMP, adenosine monophosphate. So monophosphate beta gamma. How to make that? Okay, and then the other problem, so I'll leave that structure on there and get rid of some stuff. And then we can use most of the paper, and I can stop using the board. We want to be able to make that. So if you recall back here, in the first reaction, we call it the first half reaction, actually half reaction. Biotin plus bicarbonate plus ATP makes biotin with CO2 attached to it, CO2 minus, that's N-carboxybiotin, plus ADP plus PI. Okay? That's what happens up in the first half reaction. Now, this phosphorus here, this is the gamma phosphorus. So any chirality that we put here ends up there. So if we're lucky enough to be able to synthesize this and know its chirality, like R or S, then we have to be able to, and now we have to be able to, this is going to be, this, okay? And we have to then determine, is it this or is it is it R or S? I'm not sure which is which. But is it this enantiomer or this enantiomer? And how are we going to figure that out? So now this is a long story. This took 20 years of research between a dozen research groups around the world, many in Germany, some in England, many in the States, to put together this. I will call it a technology. It allows you to be able to sort of do this, but there's a lot of chemistry involved, and it took 20 years of research to get it to a point where it works most of the time. So the real point of the seminar is to describe this. okay, how we make it, how we make this compound, and that doesn't take very long. It's on one handout. And then what do we do with these? Okay. Now there's another. So that'll take another hour. We've gone an hour. We'll do one more. Now, there's another big question here about chirality, and that is we want to let's determine the chirality here. If this is O16, then we have to look down here, and the priority is this is determining the configuration of a chiral center. So this would be 1 because it has the biggest mass. This would be 2, and this would be 3. And if I'm looking down here, then 1 to 2, 2 to 3, that's counterclockwise, and that's S. So this is the S molecule, and this is the R configuration, okay? So we've made this, and we know that this is here and not there. Then we do our chemistry, and we're going to somehow pick up the PI, the inorganic phosphate, and determine its chirality. But in order to do that, you also have to develop a synthesis of inorganic phosphate of known chirality. You have to be able to synthesize it and know that it's S or R, so that you can then develop an assay to prove it. It's really complicated. Suppose I have a bottle that contains chiral phosphate, okay? That contains either this or this, and I give it to you and say, determine its chirality. Okay? What do you do?
I mean, I don't have anything to compare it to, so I mean, I can't really do anything.
No. Yeah. No, I don't mean chemically, but just there's.
You can do it by optical activity of these two.
The optical activity doesn't work, at least not that I know of, because the amount of.
Unless you know ahead of time which one, whether is plus or minus.
Actually, yeah, okay, that's a good idea. Optical activity, but in order to do the optical activity, so suppose it rotates to the right. What does that tell you?
So you should have like a reference before or something.
You need a reference. That's what I'm getting at. You need to develop a synthesis of just this compound so that you can measure its optical activity, and then this compound and measure its optical activity, and they should be the opposite. And then when so let's just suppose this is levorotatory, and this is, what's the, dextrorotatory. So now when someone hands you a sample of unknown and you take its optical activity and it's L, then you know it's S, absolute configuration. Okay? So you need a standard. That's the point. So what I'm going to, I think we're going to do 3 things. I'm going to describe how you make this compound. Then I'm going to describe how we make the standard. And then we're going to describe the assay that picks the standard up that allows you to say, and it's not optical activity, it's something else. It's NMR, it's phosphorus NMR, that allows you to say it's RRS. Pardon? What is the aim? So the aim is eventually to go back to biotin and say, and take these 3 mechanisms to determine whether the first 2 mechanisms go with inversion, the last one with retention. So it allows you to distinguish, or it's a process of elimination. If the result is retention of configuration at phosphorus, then it can't be either of these mechanisms. So you can never prove a mechanism, you can only disprove alternatives. So that's the aim. Now, there were lots of other aims, but with regard to biotin, it was just that was the aim. Okay? So if you turn, yes?
which mechanism looks quite complicated. Isn't there like in more simple way, like IR for example?
20 years.
An IR for a mechanism? You're only looking at this, you're only looking at stable compounds, like the starting material or the product. The product is the same in all three cases. So no,
Intermediates are different.
yeah, but they're short-lived. And I don't think you can't get any spectroscopic information. Yeah, like the intermediates that are shown here, they're too short-lived on the enzyme. Now, that doesn't mean that somebody, with a fast laser couldn't do something. But anyway, and okay, so this is 1985. Maybe there's a more modern way.
But inside an enzyme, you're going to have a hard time doing a fast IR
Yeah.
inside an enzyme.
But I don't know the exact current state of the art. So it's a good question, but yeah. So if you turn to page 3, this page here, so this describes the chemistry, and I should say it is, if it's photocopied in here, it is from a journal. It's actually a book called Methods in Enzymology. So Methods in Enzymology is published once a year, book about this thick, and that people write. It's like organic synthesis. Do you guys use orgsyn.org for synthetic methodology? It's like that for enzymatic reactions. So it's guaranteed to work. So that's what this is from. And so here's let me erase this, and we can work our way through it if you can read it. So for example, what's going on from the first, approximately, what's going on from the first furan ring to the second one? What's going on there? You have deprotection. Now you have to look over on carbon 5. It doesn't come out very clear there. But what's going on at 5 prime?
One hydroxyl.
It's got 2 there now. So what is that?
Oxidation.
It's an oxidation. It's really an aldehyde. I don't know why they wrote it that way, because they're biochemists or something. But so the first what are the first conditions? Dicyclohexyl carbodiimide and DMSO. It's an oxidation. It's described a bit down here. It's a Pfitzner-Moffatt oxidation. It is, the words are down, well, the reference at the bottom, isn't it? A Pfitzner-Moffatt oxidation. So it's a mild oxidation that takes a primary alcohol to an aldehyde, if you do it right, and doesn't over-oxidize it to the acid. So and then H plus hydrolyzes the ketal, because you don't want to oxidize those you don't want to oxidize those secondary alcohols to ketones. So that's why the protecting group is there. And then what do? What is number 1 on the second arrow? It's water. It's O. Just a minute. It's O18 water. That oxygen is black. It's O18. So it's H2. So now, when you take an aldehyde and you treat it with O18 water, what happens? You get isotope exchange. You form the hydrate, which is why they wrote it as 2 waters, or two OHs. You get the hydrate, which will always eventually, O16 will leave, so you get, well, it's a question of dilution. If you have lots of, so you start with this compound, COH, OH, R, and you treat that with H2O, that will eventually go to CRH, OH, OH. This is really equivalent to this And so this will add to that through the mixed hydrate and eventually through dilution. And this is really equivalent to that. So that's how we put the O18 in there. You can't do it with the alcohol because that, I mean, you could do it because the water is not a leaving group, or the OH is. So you do the aldehyde, and then the next step is sodium borohydride, which reduction back to the alcohol on 5 prime. Now you react that with PSCl2. Now, so here you probably not. So PSCl2. What is? Are you familiar with PO? That's a 3. POCl3. Have any of you used that? That's phosphorus oxychloride. It's a dehydrate. It's a coupling agent. It's used in, and so this is simply PSCl. It's this. If you think about it, is really the acid chloride of phosphoric acid. It's like thionyl chloride, but it's okay. So anyway, so you treat molecule 3 there with PSCl3, followed by which essentially makes this. Let me just erase a bit. Yikes. That's okay. So what happens is this OH goes to OPSCl. It loses 1 chlorine, and then you throw in, so this is, then you throw in H2O17, and that just hydrolyzes the 2 chlorines, and that gets you to the compound that is shown there. So, and where this is O, so that gets you to PSO. So now you got 18 and 17 on there, okay? And then that molecule there is the same as this molecule. So this molecule, and really what this is really AMP. It's adenosine monophosphate that has a sulfur instead of an oxygen. And it's got some isotopes of oxygen around it. Okay, so it's really AMP. So AMP can be, so then we go over to this page. And so AMP plus ATP plus an enzyme called adenylate, it's written there, kinase, okay, makes 2 molecules of ADP. So ATP transfers one of its phosphates to AMP. It's kind of like a, and the mechanism for that is shown a couple pages over in a hand-drawn picture. That's if you want to know the mechanism. It's just a direct inline, well, where is it? Maybe I didn't, yeah, so it's really not the mechanism, but it's shown at the very last page. Adenylate kinase is just what I wrote there. And really, all that it is that AMP is that this attacks ATP and is phosphorylated. Now, that reaction would have been studied, and it's known to go with inversion of configuration at ATP, but that's not important for this thing. So that, but you with me now? So that now makes this molecule right there. That's ADP. okay? That molecule is then coupled with the one on the left that is kind of like AMP, but it's got a protecting group on it. It's got an acetal at the top, and or I guess it's an ortho ester, I think, or something. And so you and with the action of diphenyl phosphochloridate, so let me just, that's another coupling agent. And I don't know the precise mechanism, but diphenyl phosphochloridate is this, is POCl-O benzyl, I think. Hope I'm right here. I think it's this compound. Diphenyl phosphochloridate. O-phenyl, right there. You think? Yeah. So what happens is, and I don't, now, one of the phosphoruses on one of those two molecules, it's a coupling. Just a minute. Let me get this right here. Yeah, one of the phosphoruses. Let's say the molecule on the left, O, but we might be able to, goes here and kicks this out. Kicks out chlorine, and that makes an intermediate. This is the molecule on the right, and that makes this guy, R, O, P, O, P, O this, and then the molecule on the left comes in. That would be the ADP, and it comes in and basically reacts here, because this is now a decent leaving group, because it's just a monoanion. It's a coupling reaction. It's coupling the two phosphates together. I don't know if it activates the molecule on the left first or the molecule on the right, but it works, okay? So that makes the molecule shown below there, the third molecule down, which basically has a bit of adenosine on the left and on the right. And that molecule is then, I think I forgot a step up here. I forgot a really important step up here. We'll go back to that. And then, yeah, really important step. So that molecule here is then treated with pyruvate. And pyruvate, as you know, cleaves between carbons bearing hydroxyl groups. So it basically slices off the adenosine moiety on the right, because that's protected, and then the acid hydrolyzes that orthoacetate and then reprotonates the hydroxyl groups. So basically what we did, I have to tell you a really important step up here that I glossed over, but we basically built up the chirality on the structures on the left. We built up the chirality on the alpha phosphorus really close to the adenosine. But we ended up then transferring it over and then cleaving the bit off, and now it's at the other end. Now it becomes the gamma phosphate. So the chirality was in close. Now it's outside. Yeah, that's okay, because we're going to use O16 in the chemistry.
No, the enzyme only gives one stereochemistry.
Okay, so we missed a point up here. Let me see if I can just. So I talked about adenylate kinase. So adenylate kinase takes the top molecule and makes, which is AMP, and makes ADP. Okay. Now the next enzyme is called pyruvate kinase and phosphoenolpyruvate. Now those mechanisms are given at the end in my handwritten mechanisms. And the point is, this is the most subtle point of all. How are you guys doing? You're hanging in there?
Good, but I have a question.
Yes.
Just on the previous steps, it's just a silly question.
No.
For PSCl3, like usually POCl3, it can be used to transform OH into Cl. So with PSCl3, there is no such similar activity?
With this guy?
Yeah, because you're using it with the alcohol at the 5'. So this could be like a decided product, or it doesn't form at all with PSCl3.
So-
Because it may have different properties. I don't know.
So
SN2 with the chloride.
yes. So your question was in this.
My question is that with POCl3, like and this part here, the one,
Yeah.
and the alcohol at the 5' position.
Yeah.
Like usually when you put an alcohol with POCl3, it's the method used to transform OH into Cl group.
Oh, I see what you mean. Yeah. So so it kicks out the chloride, and then the chloride can kick it out. Yeah. So yes. Well, you have to do it carefully. And so you end up with this, and before chloride can come in here and do what you, is that what you meant? I don't know, but under the right conditions, instead of this doing that, water, O17 water comes in and hydrolyzes it instead. It's a bit. I don't know the exact. The conditions are given in this experimental.
How does is that which you said was iodate?
The pyridate?
Pyruvate. How does pyruvate differentiate between which?
So pyruvate grabs the diol. I can't give you an exact mechanism, but on the what it does is it grabs this thing, and the I is in some kind of +5 oxidation state and comes in here and eventually cleaves there. It cleaves between OH groups, and it basically.
Actually, they'll just cleave to the diol, and then the base eliminates it to the dialdehyde. Right, so they cleave to the dialdehyde.
Do you?
Yeah. And then the base is going to eliminate the phosphate at the 5 position. It's going to use the elimination.
I.
Oh, okay. So instead of me thinking about it actually attacking the CH2, I should think of it attaching to the hydroxyls
At the bottom.
at the bottom. And okay.
Makes an aldehyde, and then you eliminate the beta phosphate.
Okay. Yeah.
That last step with the base.
Yeah. So if your phosphorus is here, there's an aldehyde. It's acidic. You mean something like that. Okay. Let's move on. Let's move on to the next bit. We're going to see this enzyme again, this pyruvate kinase. That's a really important step here. But let's move on to the next bit. So the next bit is now where is it? Okay. So the next bit is we're going to look at scheme 1. Okay. And scheme 1. So scheme 1 starts with the compound with this modified AMP. So it's got sulfur at the top on the phosphorus and 2 O18s. And that could be made, for example, just I think I've sketched in at the very top there, how that would be made from adenosine, PSCl3, and heavy water. So you have that compound. So now that's AMP. So now what you do is you operate on that with diphenyl chloridate again, and phosphate, it's O17. Okay, so that makes this same kind of, did I put it down here? I thought it sort of makes the same intermediate here, except this is O, P, S, O, this is O, and this is, so, and then our O17 water comes in here and kicks that out. So now we have, this is this O, that's 16, this is 18, and we bring 17 in. So we get two molecules there, which are basically ADPs. And what we have here is we have what's called the A form and the B form of ADP. What is the difference? What is the chemical, or the structural difference between A and B here? Now, I'm going to erase it and try a bit here to try to show you some. What is the difference between A and B? If you go back to the first molecule, and you're going to react that with your POCl, this, O-phenyl, okay, then these two are the same. And this guy, so you have a 50-50 chance of this one going here and displacing that, or this one going and displacing that. And so when you come to this intermediate, this guy is either on this oxygen or on this oxygen. And it's 50-50 mixture. And then when water, the O17 water comes in and hydrolyzes it, either the PO8, sorry, not the water, the PO17, it's either basically at the front or the back. So that phosphorus there, that alpha phosphorus, if you like, is now chiral, because it's got sulfur and then O17, O18 in opposite positions. So that's chiral, and it turns out that those two compounds, and it turns out so that you now treat that with an enzyme called Pyruvate kinase and Phosphoenolpyruvate, or PEP. That's another high-energy phosphorus compound whose mechanisms are shown at the back. But it turns out that it was shown that pyruvate kinase has a preference for the A form over the B form because of the chirality on the inside phosphorus. It's a preference. It's something like a 4-to-1 preference. Now, the difference between A and B were eventually determined by crystal structure, I believe, of something like cobalt salts or of this ADP, and the crystal structure was determined, and it was shown that the sulfur's here and the O18 is there, and not at the back, sort of thing. So that was a crystal structure determination, and pyruvate kinase has a preference for A over B. So pyruvate kinase takes ADP, turns it into ATP. So that's why now on the left, that molecule is ATP, and the molecule on the right is unreacted B form. Okay? And those, so what you have now is ATP and ADP, and those two molecules can be separated with ion exchange chromatography. ATP has sort of 4 negative charges, and ADP has 2 or 3, depending on the pH that you run it at. So they can be separated, and that's why that line is in the middle. Because at that point, you can separate them, and now you've separated, you've got some chirality separated there. So if you follow the compounds on the right, which is basically the B form, that is treated with periodate. That's with sodium periodate and base, and that cleaves off the furanose ring, leaves you with that compound there is what's referred to as pyrophosphate, which is two phosphates, phosphate, pyrophosphate, triphosphate, okay, where one of the phosphoruses has a sulfur on the end, and the other one has oxygens, but they're O17s. And it turns out that in biology, so it's this molecule, P S O this O P O, this is a 17, this is 17, 17, 17, is that, there's an enzyme in biochemistry called pyrophosphatase that cleaves, hydrolyzes pyrophosphate to 2-phosphate molecules. It's an anhydride, so it releases some energy. So biology makes use of it. But it turns out, because this is not symmetric, water prefers to come in here on the oxygen side, not on the sulfur side. So so this is the leaving group. Now, did I draw it correctly? I don't think I did, actually. So when pyrophosphatase acts on that compound, it gives phosphate of known chirality, R, if you follow it all through. If you follow the other line of reasoning with some enzymes, you get the S. And because of the known configurations of the A and B form, you can be certain that one is S and one is R. So that's your standard, okay? So those are your standards. So there's only 2 more things to do here.
In the end, it was an enzyme that could separate them.
Sorry?
So in the end, it was the enzyme that...
Yes. It was the enzyme that separated A and B.
Okay.
Yeah. Whose mechanism is given at handwritten notes at the back.
They just tested different enzymes, or they came up...
It was 20 years of research. Okay. Yeah, little contributions, yeah.
But remember, you have the adenosine, so these are diastereomers. So they really
yes, they are diastereomers, yeah. Because the adenosine's got its chirality, only one difference here. So yes, it's not surprising. Anyway,
but not surprising.
yeah. So those are your 2 standards. Now if you turn the page and you go to scheme 2, okay? So scheme 2 does this. You start with one of your standards that you've made. And let's say we're starting with the R standard, with sulfur and the oxygens arranged in that fashion. Now this is an enzyme worth looking at. So you have to be able to, so what he did was he picked he wants to incorporate the phosphate into a biological molecule. And it turns out phosphate is a substrate for the enzyme glyceraldehyde diphosphate dehydrogenase. So why don't you just go to I think it's the back page of the handout, page 9, which, shows the mechanism. It starts with glyceraldehyde. It basically starts with an aldehyde, okay? Do you have it? It should be circled as 9, maybe up here. There should be 2 pages of handwritten notes. Second page. So it starts with an aldehyde, and basically what it does is the top equation just shows it. So in the presence of NAD plus and phosphate, it makes that mixed anhydride. Carbonyl oxygen phosphate. Okay, now how does it do it? Well, there's an enzyme, so this sort of shows it. There's an enzyme where a sulfur group adds to the aldehyde. That O minus then comes back and reduces NAD plus, makes a thioester, and NADH leaves. Phosphate now attacks the thioester and gives the sulfur back to the enzyme, and you now have phosphate incorporated where the carboxylic acid, where the aldehyde used to be. So it's oxidized it with the help of NAD plus, and phosphates come in. Okay, so that's what scoops up the phosphate. And so, of course, because you have 3 different oxygens on the phosphate, all 3 oxygens, O16, O17, O18, could attack that ester intermediate. There may be a small isotope effect, but it's negligible. So basically, you get 3 compounds. You get those 3 compounds where the only difference is which oxygen is, whether it's O17, 17, 18, or 16. Okay? So you have those three different molecules there. What's the next enzyme? Phosphoglycerate kinase is an enzyme that takes ADP, and this is a high energy molecule that we've just made here. It's an anhydride, so it can actually so this substrate can phosphorylate ADP. So you're working with the mixture, you're not separating them, and with magnesium ADP and phosphoglycerate kinase, you make these ATP molecules. These are now all ATPs. It shows the chirality on the gamma phosphate, all 3 possibilities plus ADP. So you make all three, and you have them together. They're not separated. Well, then you react it with adenylate kinase. And we already saw that. So these are ATP molecules. Adenylate kinase transfers, where am I? Transfers, that's an ATP. Adenylate kinase transfers that chirality on those ATP molecules to AMP. So now the chirality is in the beta position, or at the outside position of AMP, and phosphoglycerate kinase then rephosphorylates that and gives you the 3 molecules at the bottom, 1, 2, and 3, where the phosphorus with the sulfur on it is in the beta position. The gamma phosphate is phosphate. The inside phosphate is, the alpha phosphate is phosphate. So the beta phosphate has sulfur on it. So if you look at it carefully, they all have sulfur, and it has O18. So the first one has O18, so-called bridging to the gamma phosphate. Number 2 has no O18, it's got O17. And number 3 has O17s and no 18. So it turns out, what you do now is you do a phosphorus NMR. This is essentially ATP. And you do a phosphorus NMR. So the phosphorus NMR, the phosphorus NMR, so you have adenosine, O, P, O, P, O, P. Phosphoruses couple with each other. They have a spin of a half. So this phosphorus here is a doublet because it's got one neighbor here. This is a doublet. But this phosphorus here, the beta phosphorus, it's a triplet because it's got 2 neighbors. So it basically looks like this. Okay? Now, it has sulfur on it, so it's unique. And now you have, it turns out that if the molecule contains O17, the O17 has a quadrupole moment or something, and you cannot see the phosphorus NMR does not work very well with O17 in it. So molecules 2 and 3 have O17, and you don't see them. So you only see molecule 1. So that's the first thing, is you don't see the O17 molecule. So although you have 3, you don't see 2 and 3. You only see 1. And so the difference is so 1, what you're really comparing is molecules 1, and if you were to take the other molecule, if you look at scheme 3, and scheme 2 started with R, scheme 3 starts with S, then you end up with molecules 4, 5, and 6. Okay? And again, if you look at 4, 5, and 6, 5 and 6 have O17s in them. So you don't see it. You don't see those. So you only see molecule 4. What's the difference between molecule 1 and molecule 4? Molecule 1 has the O18. 1 is 18O in what's called bridging position. It's bridging the beta and the gamma phosphorus. So it's basically here. And this is this is O. Whereas molecule 4 has the O18 in the non-bridging position. So 4 is O18 in so-called non-bridging position. So O18, the O18 gives an isotope effect. It changes the chemical shift slightly for that beta phosphorus. For this one, where it's bridging, where it's non-bridging, the non-bridging one, that would be when it's out here, okay, non-bridging, has a big effect. So it shifts them all, it shifts the whole thing down like this. It shifts it to the right. Whereas when it's in the non-bridging position, its influence is only partly this way. It also affects this way, so it's not as big an isotope effect. So this would be for 4, whereas I've drawn the two close together, whereas 2 would be here, here, and here. If you turn the page over, you'll see what I mean. So this last page is the triplet. Basically, it's the triplet expanded for the beta phosphorus. So if you look at the top spectrum, it explains what the peaks are. So the left-hand peak is O16. So all the left-hand peaks in those things are due to the molecules with O16. The next molecule contains O18 in a bridging position, so it moves it a little bit to the right. The next peak is the O18 to the non-bridging position, and the biggest peak is O18 in both positions. So it's like a double isotope effect. Okay? So that's how you tell the difference. Basically, if you look at B and C here, B and C shows that we'll get this right here, that the bridging position is a little bit higher than the non-bridging position, whereas in C, the non-bridging position is slightly bigger than the bridging position. So spectrum B was made from spectrum B was obtained from molecule 1 that has it in the non-bridging, or has it in the bridging position, whereas spectrum C where the right-hand peaks are a little taller, was made from molecule 4. And so you can tell them apart. You can tell the R and the S apart by the phosphorus Nmr as to which of those two peaks is higher than the other. The reason they're not distinct is because a lot of the chemistry is not perfect. So long as there's a slight difference, 50%, then it works. So in the end, just to recap here. Well, any questions? I know you're tired. I've been blasting you.
No, it's cool. I think it's just
Nothing compared to what we do to them.
Okay, good. So in the end, let's just recap and go back to biotin and what Knowles did. So Knowles made the chiral ATP. Okay, and I should draw it, which is shown on page 3. So he went through that procedure from methods in enzymology. So he made this compound. He made adenosine ADP with OP sulfur O. So this is O17, this is O17, this is O18. So he made that compound. He then reacted, that was his substrate for biotin and bicarbonate and the enzyme, and he got biotin CO2, N-carboxybiotin plus ADP plus PI. And he wants to know what happened there. He wants to know because, did this come in here? Did biotin come in here? What happened? And that goes back to the very first page. So he grabs this and he goes through, he uses basically scheme 2. He picks it up, he incorporates it into that organic molecule using glyceraldehyde diphosphate dehydrogenase, and he makes all 3 molecules. P with and I should say this is chiral. What this is P S. Let's put it this way: O16, O17, O18 of undefined chirality. But we started here chiral, so we want to know what this is. This made all of the molecules shown, and then he goes all the way down to either 1, 2, and 3, or 4, 5, and 6. He takes the phosphorus Nmr, and so if you look at the first page again, you look at the first page. At this NMR spectra, this peak, and this peak, and this peak, those are from P04. That's those are from the this is from AMP PO whatever PO3. This is from this molecule with oxygen here and here. There's lots of that there. What's important is that the next peak, that this peak is bigger than this peak. And that peak is due to, as he says, that's due to the bridging position. Bridging. And this is the non-bridging, bigger isotope shift. Because this peak is bigger than that, he must have picked up the pi that was in there must have been, it's like spectrum B, it must be R. So only the R compound, only the R compound here would give this peak, these peaks, bigger than the other one, and which implies that only one O16, say from bicarbonate, went in here and inverted that. So the result is that this reaction goes with inversion of configuration at the gamma phosphate, not retention, and that rules out mechanism 3.
But now how do you differentiate?
1 and 2? Read the paper. He makes some arguments. Number 2 is kind of unprecedented as well. He gives some very good arguments. And so he favors number 1. He favors number 1.
I mean, this phosphate intermediate, you might be able to observe.
The one we drew, and yeah, or the one at the top, yeah. So I've just tried to to describe this sort of bit of technology, this business of chiral ATP, how to, and it's made with a combination of chemistry and enzymatic reactions, and yeah. I don't know. I guess I'm getting paid for 2 hours, so. But
So lots of questions here. I'm going to steal the microphone so people elsewhere can hear the questions. So anyway, thank you for some marvelous work, and you see the amount of work it is to figure out what a real mechanism is, right? On paper, we can draw a lot of things. There's a lot of hypotheses, whatever. So physical organic mechanism is the true mechanism. You see what type of effort it takes to show that it goes this way and not another way, and how important that is. That sometimes you can just say, well, who cares, it goes however. It's something that for many years got lost because people just thought it was too much work. And then we're starting to realize we don't actually know how any of the chemistry really does work. And so now we're starting to really come back to this type of work. And sometimes the solution seems, let's go use the 1000 megahertz NMR and the super duper synchrotron thingamajiggy. But ultimately, this type of chirality, this type of experimental, very rigorous, very hard work, but ultimately will have a clear result that says, okay, this went with inversion, this did not go with inversion, is worth the tremendous effort it is to get to that point. So if any of you have any questions,
I have a question.
I teach this in my third year bioorganic class. It would normally take me at least two or 3 days, probably 3 days. It would take me a week, 3 classes, because they're third year undergraduates, and you got to go slow. I mean, there's a lot of information. So, yeah.
Well, as a second year undergraduate who I've never taken organic chemistry before, but I understood this, which surprised me because I didn't expect to. But ATP is used for so many things in the body.
Yes.
What kind of implications do you think? Number one, creating chiral, organic, chiral phosphates could have on really understanding the other processes in the human body that use ATP.
That's a good question. you know, like I say, all our muscles. The main reason, well, I mean, our muscles consume kilos and kilos of ATP a day.
17.
Is it 17 kilos? You know,
No,
so
same ones over and over.
yeah, we make it in our mitochondria, and we consume it in our muscles. We consume it in our brain. The few biotin reactions that occur, we consume it, and so on. But so I don't, you know, that's a great question. I forget just now. You'd have to go back and look at how muscles work with myelin and yeah, and moves it along, and things things sort of walk down the sheath and consume ATP. So I mean, if you really wanted to know some more details about those processes, this might, because some reactions do go with retention. In other words, the phosphate gets handed to one thing with inversion, and then handed back to something else with inversion again, which is overall retention, and then gets hydrolyzed to phosphate. So if you want to know that, then you may have to do the hard stuff and make that compound, and then pick it up and analyze it. So there's lots of possibilities. I mean, and lots of things have been done. If you notice, even the subject of the paper on page 4, analysis of chiral inorganic phosphate, 016, 017, 018 thiophosphate, and the stereochemistry of the 3-phosphoglycerate kinase reaction. It turns out that one of the enzymes used in the reaction, its stereochemistry was not known. But once you, and I just forget which step it is, but by using it in this analysis, it can only go one way. In other words, a piece of the puzzle fell out for that enzyme. You'd have to go back and just look. It's either scheme 1 or scheme 2. And it's in scheme 2. It's the second reaction, and so on. So I would say it helps elucidate mechanistic studies. Questions?
So I'll try not to get caught up in it, but I'll probably fail miserably.
I mean, this research has been like 35 years ago. Is there any recent arguments between scheme 1 and 2, some recent developments, or is it like the new thing to study now?
Yeah. Oh, here, yeah. As far as I know, mechanism 1 is the preferred one. Knowles argues strongly against 2, which he elaborates on. And there has not been a whole lot of interest since Knowles left the field and died. Was he around when you were there? Yeah. Yeah. What's that? Did you? Yeah. Not a whole lot has been done. People have lost interest in biotin. There's only myself and actually, and a couple people in the States who I'll show some crystal structures of tomorrow have remained interested in biotin. So that's the mechanism 1 is the current. Even now, yeah.
Okay.
Now I should say that biotin involves carbon dioxide, and I've been trying to think for some time. We're all trying to find carbon. How to remove CO2 from the air, carbon sequestration. And so, here's an enzyme that's evolved for millions of years. Is there any way we can take advantage of it somehow as a carbon sequestration technology? But so it's worth thinking about. That's why research, I believe, on enzyme cofactors that have, taken 1 billion years to evolve they're really worth looking at, because we can learn lots of things from them. What I'll describe tomorrow, as I said, is is an idea of what the sulfur is doing. I think the sulfur is really interesting. And the whole business, I drew some arrows from the nitrogen, as Knowles does as well. All these arrows from like that arrow there, that's a big problem. Because urea and nitrogens are not that nucleophilic. And he comments a bit on that. And I think that's where the sulfur comes in. The sulfur comes in and helps activate that nitrogen. Lots of people have speculated on that as well over the past 40 years, but that interest has dropped as well. I'm sort of about the only one interested in it still, and I think I have a neat theory. And whether my theory about it is wrong or right, it has helped me develop other chemistry. So, you know, I think that's valuable.
If I may, so of course lots of people are very interested in biotin by its interaction with avidin, which is an extraordinarily 10 to the 18th binding constant. Are there any notions of how, what's special about this molecule to get that kind of an interaction?
Well, I know the crystal structure, has been solved for it, and there are lots of hydrogen bonds between the NHs and the oxygen and even to the sulfur.
I can show you lots of hydrogen bonds to glucose, and it's not anywhere near 10 to the 18th.
Well, actually, I mean, I don't know. There was a woman in California, Davis, that solved some structures a while ago. I think it was mainly just because she was a protein crystallographer. I'm not sure. I got to look that up. Yeah.
It's just one of those interesting things. We're far from understanding protein binding, and this is one of the really interesting cases. You can look at the interactions, but you'll find a lot of similar interactions, and this is one of the strongest interactions that nature's chosen to do. But unfortunately, that's sort of the part that's sucked up all the attention. But its role as a cofactor has been, largely neglected.
Yeah. Of course, biotin has an affinity for its enzymes. It has to be recognized. And some of the same hydrogen bonds are there in the crystal structures. But it can't be tightly bound, or that would be the end of the chemistry. It has to go in, then it has to come off. So, there are some. I'll show you a structure tomorrow where biotin goes in. I'll leave you with another question here. Biotin goes in, bicarbonate, ATP, and the whole enzyme has a big conformational shift and puts a lid right on the whole thing. So they have the crystal structure of uncomplexed biotin carboxylase and closed in biotin carboxylase. And so one of the thinking, I'll just pose another question to you. And you can answer this too.
Here, let me give you I'll go around the other way. Microphone.
So here's something else to think about, and it's CO2 chemistry. We have we have water and carbon dioxide as a gas, and carbon dioxide, of course, can go in here, and it can now be hydrated, or it can be dissolved. There's some dissolved CO2, and of course, this can go on and react with water to give bicarbonate. Okay. And so if you want to carboxylate something, so let's say you have acetyl-CoA carboxylate. You have CoA S. Let's draw it enolized OH. So this is enolized acetyl-CoA. What's your best carboxylating agent? I mean, so let's make it an enolate. This is minus. What's your best electrophile? CO2. CO2 is neutral. It's like I said, it's got those two oxygens. You know, this has a big delta plus. So that's a great reaction. This is not. Okay, so nature, in evolving its enzymes, if it's doing carboxylation chemistry, for example, in green leaves take up CO2 and turn it into sugars. Well, okay, now, so in water, the concentration of this is something like 10 micromolar. So there's about 10 micromolar in equilibrated water of CO2, whereas this is 200 micromolar. Okay, so there's more of this than this. If you're an enzyme and you want to carboxylate something, and you're evolving, which do you choose? Or, you know, which do you start to evolve around? The less abundant but more electrophilic water, or the more abundant but less electrophilic bicarbonate. And it turns out enzymes do both. In photosynthesis, it uses CO2 directly in the green leaves of plants. The CO2 goes in, and ribulose 1,6, I forget, rubisco. Rubisco is the enzyme that absorbs CO2. And the green leaf of plant is full of rubisco. It has to be full because there's very little CO2 dissolved in the cytoplasm. So there's lots of it, whereas biotin-dependent enzymes evolve to grab this. And so essentially what is happening is that ATP is essentially, I think, is dehydrating bicarbonate. Okay. Now the other thing about it is this. CO2, I describe it to my class as, you know, it has no dipole moment. It's like a greasy watermelon. Enzymes don't recognize it very well, you know. Whereas bicarbonate has a negative charge, so if you have a positive, you know, there's hydrogen bonds, there's lots of things for an enzyme to recognize it. Whereas this guy is just, how do you grab it? You know what I mean? There's no polarity. And I describe it as a greasy watermelon. We would play games with, you know, you take a watermelon and cover it with Vaseline and try to catch it. It's very hard. Whereas this guy, so I think that's why the biotin enzyme, you know, like I said, there's a crystal structure that, how to draw this, let me see. That everything goes in here. So this is open, and then when it's closed, and then after everything goes in there, this lid comes right down on, and the pocket's inside there. And I think the reason that it closes down is because it makes CO2 there. And if you go to all that energy to react, if you burn a molecule of ATP to make CO2, you don't want to lose it. So you have to clamp it in, and then it reacts with biotin, and so on. So I don't know. Those are just some considerations of CO2 versus bicarbonate.
So I want
Yeah.
to make sure you're saying that the biotin evolved to grab onto all right, so rubisco has no biotin.
No, that's totally separate, but CO2 is the substrate. There's no bicarbonate.
In biotin,
It's been shown it's been shown that bicarbonate is the substrate.
Okay.
It was shown in this fashion. It was shown by someone who took O18 labeled bicarbonate. Okay? This is a really neat experiment. This was done in the early 60s. If you take bicarbonate and biotin and ATP, you end up with CoA, sulfur, COOH with these are O17s here, and PI contains one of the O18, excuse me. So these three end up here and in the PI. So the question is, how does that happen? How do they distribute themselves? And the only real, one logical way is that at some point, this reacts with ATP to make that mixed guy. So this would be here, here, P, this, okay? And then either, like I said, either this decarboxylates, and that puts one of them here, it makes CO2, or the nucleophile comes in here and kicks that out. So at some point, it's pretty sure that at some point, bicarbonate has to come into contact with ATP to distribute the O18 that way. And that was determined by mass spec, where the O18s were. But sorry, I think I interrupted you.
No. You helped me out a little bit. So a lot of this is like, but I'm not
Yeah.
kind of confused.
So it's been a fertile area for.
So how about some pizza? So we have some pizza, and for those, I apologize to have put this during Ramadan, so those who want to stay around long enough to be able to eat pizza, not quite, still a while. But at least come and chat with Dr. Grant. And if any of you are interested in having lunch with him tomorrow, we have a slot for lunch. So if you are available, let me know, and when he come, allows you to discuss a bit more. And since we're here as part of the master, normally we stick them with a bunch of faculty members who are much less interesting. So
Sure.
I think it'd be more fun with you guys than with that. So why don't we go back to the other building? You can all ask Fatima to let you in, because she has she's programmed into our little beeper. And let's head over that way. Let's see.